Okay, we start up again. So I want to show you where you can find a little bit information. You have chapter 3 in the book by Versteeg, which then is an okay description about turbulence. Let's see, where are we? Somewhere here. And it's roughly the same that I have been talking about. So you have more information here if you want to. Now, something in this one is worth mentioning. Let's see now. Where are we? Here we are. It's called the law of the wall. That's something we have to look into. So either you can read it here, or I will show you another version of it, a little bit easier. But the law of the wall, sort of some recipe how the turbulence behave close to walls. And that's something that we can use in our modeling. So we will coming back to that one. Here he starts to derive, say, the Rans equation, Reynolds stress equations, with the mean velocity field, mean pressure field, and then you have these Reynolds stresses in addition. And he writes everything out here, quite complex. So the entire set here then should look something like this. And okay, if you have the Reynolds stresses or a full Reynolds stress model, then yeah, you have to put in the functions here, and so on and so forth. So a full Reynolds stress model, way too heavy. So we then will use, say, the more classical equations. Not the zero, that's too simple. But Spallar Almaraz, that's something you should know. Two equation models, K epsilon, K omega. And then, as I told you about, this ASM model instead of a full Reynolds stress model. So the ASM, definitely something you should keep in mind. And then here he should now go into the detail of the different models, and here we have the K epsilon. So if you want to see at least an example how such an equation may look like, then here, not that one, that's the exact one, which you just simply can forget because it's not possible to find it accurately anyway. So same with this one. No, you can't use this one in practice. So we model it away. So the K epsilon model equations, that's a different story. So here then you have the Prandtl-Kolmogorov equation, the sort of the last coupling needed, finding the eddy viscosity based on K and epsilon. And then here you see examples for such model transport equations, how they can be derived. And yeah, the different constants here have to be played around with. Not so fun. And also here you see you divide by K. Laminar flow, no, that's not good. But anyhow, going into the details here, that's not for us. I mean, the models are available to us, so we are just going to use them. Here you have this sort of a standard set of the numbers, parameters normally used in the K epsilon model. Boundary conditions, that is a big question. We haven't started looking into that. That is very tricky indeed. Now, say for instance, you need to set in, if you have an inlet, you have to specify the turbulent values for the inlet. I mean, if you have a problem, you're sending in a velocity or something, that's not a problem. But you need to put some values for K and epsilon at the inlet. How the heck are you going to do that? Well, here is one way to find, say, some estimates of these values. There's one recipe. You have several others as well. You can also find them in the home page when you look at the open form material. So inside userguideopen4.com or userguide.org, you will also find these recipes, and also inside this one. I'll have a look at that one later. Turbulence in open form. So, but here at least one recipe for K and epsilon. I think you also have another one for K and omega later on here. Here, the Spalart-Almaraz model. Just one transport equation for the eddy viscosity. A lot of modeling there as well. And then the K omega. And again, modeled, everything is modeled. And here the K omega SST. This was a mix between K epsilon and K omega, trying to use the best of both worlds. So it's sort of a hybrid model. Actually quite good model. And the ASM model, let's see now, he has some examples how you can find the different Reynolds stresses based on, for instance, K and epsilon. So he has some nice, judgments of the different models, where they are good and where they are bad. So this can be nice to know. So the ASM, yeah, has some advantages, also has some disadvantages. So, and he does the same for K epsilon and K omega, if I recall correctly. Let's see. Come on, he talks too much. Here we have it. For the standard K epsilon, for instance. Excellent performance, well, excellent for many industrial relevant flows, and is well established. But we know there are some problems where he will give very bad results. Rotating flows, when you have a flow in a curved walls, along curved walls, this one is terrible. It's best for, say, external flows, flow around something, not inside something. And then a full Reynolds stress model as well here. So you have a lot of information for the different models. If you're interested, be my guest. So I'm not going into the details here. Let's jump to the short version. Turbulence in open form. How is this done in open form? Starts with some nice figures. This is a classical figure. Everybody's using this image from a wind turbine park. Very nice indeed. A jet, water jet, a bullet, Mach 1.5. And here you typically see the turbulence scale inside such a wake. Ooh, they are very tiny if you want to describe everything. No, we have to model it away and make it easy. Yeah, I won't go through this one in detail. You can have it, you can read it yourself if you like. Now that one is quite important. Yeah, we model, and we know any model is going to be wrong, but how wrong? Maybe it's something we can use from the result anyway. So they don't have to be terribly wrong. Yeah, also some k omega expressions here. Let's not talk too much about that. But here, the law of the wall. Law of the wall. This is something that is quite crucial for us. We have to sort of understand this one. The law of the wall, it consists sort of two parts. The innermost part, when you are very close to a wall, then we have actually a laminar velocity profile. Then the flow becomes laminar. But this is only on average. In real life, the turbulence is produced close to the wall, so there you have actually a lot of action, a lot of turbulent motion. But quite rapidly, on average, you will get a laminar velocity profile, very close to the walls. Further away from the wall, you can actually find such a logarithmic connection there between the distance from the wall and the velocity. And we know that this actually is correct. It's done a lot of experiments. So it fits quite nicely, actually. So we can trust this one. Now, the definition here, u plus, that's the velocity. It's just been scaled, so it's non-dimensional. And the y plus, that is the distance normal to the wall. That's also been scaled in this way. Now, first, the shear stress on the wall, tau. That one you should know from basic fluid mechanics. So this one, I mean, it's the derivative of the velocity gradient perpendicular to the wall multiplied with the viscosity. Then you have the wall shear stress. And if you divide by the density and take the square root, you will actually get meters per second. So you create a velocity out of this one. It's not a real velocity, but it's just a velocity scale. And we call it, say, the shear velocity, the u tau. So just using it for a scale. Now for the y plus. You see we use this velocity scale here. And then you have the distance to the perpendicular to the wall in meters, then divide by the ordinary molecular viscosity. You see this is a local Reynolds number with a velocity scale and a length scale. So y plus, think of it as a, say, local Reynolds number. And that's why you get these numbers for y plus. Sort of is non-dimensional. Reynolds numbers don't have any dimension, so that's fair enough. And when you are very, very close to the wall, here they typically call it a viscous sublayer. Some people call it a laminar sublayer, but remember it's not laminar actually. But the solution will be a laminar velocity profile. But you have to be, say, below actually 6 in y plus for this one to be correct. And then this light blue here, you sort of have to try to patch these two solutions, because here you have to be above 30 or something before this equation pops up. So in between, you sort of have a buffer layer, they call it. So now you have the problem. Where are you in your computational simulation? What's the distance from the wall to the first cell, to the first unknown that you have? If you are inside here, okay, then, then we can use this connection here, finding a reasonable boundary condition for the velocity. If you are outside here, Then we must use this equation. Then we are going to need a wall function to describe the velocity close to the wall, because then we are actually jumping over a lot of physics very close to the wall. And if the Reynolds number is too high, you can't really describe it. You can't resolve the boundary layer very, very close to the wall. Then we have an option using this law of the wall. If you are in between, you're in trouble. So you should either be here or there, not in the middle. That's something you have to check. What is my y plus along the wall? We have to find out. We have to find out. So as an image, here you now have a wall, and here is your mesh system, and you see typically you will then stretch the mesh, smaller and smaller cells close to the wall, to describe all the physics down here. And inside the viscous sublayer, you see we have plenty of cells here. So this is a good resolution of the boundary layer very close to the wall. Here you don't need any wall functions or anything like that. You have a natural boundary condition. Velocity is 0 on the wall. Done. So no problem there. The image here, not entirely true, of course, but never mind. As I said, it's actually a lot of things happening here, but we model it away. So that is, say, in an ideal world, yes, you will do it like that. Here, just a list of different turbulence models that is available. Depends on your distribution, your version of OpenFOAM, if you, what kind of models you have. The Rans family, or unsteady Rans as well, typically we will play around with these. These are more advanced. Now you're talking large eddy simulation, and even a full direct numerical simulation. Forget it. That's for, if you want to continue, take a PhD, be my guest. Here, very nice one. A quick overview over, say, the most important models that we are going to fight with in this course, at least. Spalar-Almaraz, suitable for external aerodynamics. So that's what it's designed for, and it's quite easy to use. It's only a one equation model, so it's quite cheap. And the boundary conditions and also the inlet values here, not so hard to find. Standard q epsilon, well, you should be familiar with it. It's quite robust, but we know it fails in some cases. So something you should be familiar with. This one might be better, more advanced, more modern. So he can handle, say, more cases than the standard k epsilon. Then you have the standard k omega. Much better, as I said, when you have internal flows, wall-bounded boundary layers. Then you should choose this one instead of the k epsilon. And then you have the k omega SST, sort of a mix between these two. So can also be a very, very good idea. And as a recommendation here, if you have absolutely no idea, either realizable k epsilon or use the k omega SST. Problem here again, boundary conditions, how to treat the walls, how to treat the inlet. That is now also a question. So you have sort of the choice here. Either you resolve the boundary layer. You have to have a distance of in y plus for your first cell smaller than 6. Then you resolve the boundary layer, and you can have a natural boundary condition for the velocity and also natural boundary conditions for the different turbulent quantities. You have to specify also boundary conditions for k, omega, epsilon, depending on your model. So here you have resolved it. If your Reynolds number is high, this is going to be very expensive. You need 1 million cells. Then we cheat. But then the distance to your first cell has to be big enough. Then you need actually a quite coarse mesh to stay away from the wall. You're not allowed to be inside here. You should have it above 30. That's the limit for your first cell. Okay. So it's one or the other, actually. And how to find out? What should we choose? Well, one easy way is trial and error, of course. But you have actually a possibility to check it before you start the simulation. Coming back to that. Then the boundary conditions at the wall. We have a whole bunch of different functions there for the different quantities. And of course, this is not something that we are going to look into in detail. We have a nice list here later on that you may use. Yeah, here are some examples here for the different, say, the equations, how they actually look inside the OpenFOAM source codes. And here, the K omega turbulence models. And here you have a recipe for finding, say, at least estimates. You have an opening, you have an inlet, sending in a velocity or something. But you have to send in something with these turbulent quantities. What is K at the inlet? What is omega at the inlet? You have to put some numbers there. So at least you can get some estimate here, and at least a place to start. Yeah?
When simulating a boundary layer using a really fine mesh instead of the wall function, is the refinement rate of the mesh cells relevant for the y+ values? Or?
Yeah, that's an important question. How can you resolve, say, the boundary layer decently? So you might think that, okay, my first cell, very close to the wall, I take that one very, very small. Then the next cell, well, he's rather big. That's not good. As a rule of the thumb, your mesh should be smooth and nice. So you shouldn't have too much change in area from one cell to the neighbor cell. In the old days, we said 15% change. That means it has to be sort of smoothly stretched. Nowadays, they can handle more. So you can go from, say, from size 1 to size 2. You can double it. He will still handle it. Maybe not so good. You have to check it, investigate it, find out. You have to play around with the mesh there and see, does my solution change? If I change the mesh, then you're in trouble. Which solution is right? Your headache. No, but it should be smooth. Other questions? Now for these estimates, you need some numbers here. The turbulent intensity, we have to choose a number here. And also for this eddy viscosity estimate. And I think he gives a list here. So remember, it says low, medium, high, meaning Reynolds numbers. But low Reynolds number is still turbulent, but it's just turbulent. For instance, in a pipe flow, 2,300, that's sort of the limit between laminar and turbulent. So if you have a Reynolds number of 3,000, you are in this range. Low Reynolds number, but still turbulent. Then medium, up to, say, 10,000, 50,000. High, 1 million, something like that. Depends on the problem. So it's your headache. What do we mean by low, medium, or high Reynolds number? And then you can choose some numbers here. The intensity then, for low, we say the velocity fluctuating part is only 1% of the mean velocity. If you send in 1 meters per second, then this guy here will be then 1 centimeters per second as an estimate for the turbulent kinetic energy K. And here also for the eddy viscosity. You have the same recipes, or you find the same recipes also for not K omega, but K and epsilon. You find that one in the user guide for .org, I think. It's on the homepage. The user guide for OpenFOAM. And you find it in the book by Versteeg as well. Then we have the wall functions. For the K omega, if you are bigger than 30, then for your first cell, then of course you have to use wall functions. You shouldn't go too far either, because this law of the wall, it's limited. You can't go far from a wall. Of course not. So, but it should be between these two. So you have to check the y plus value. We have some scalable wall functions here, but that's only for this K omega SST model. Then you can actually be between 1 and 300. So they have put in some automatic calculations for us there. Else, smaller than 6, that's the limit. Must be smaller than 6, should actually be close to 1 actually, to really resolve the boundary layer well. Then you can use more natural boundary conditions. So he has a list here somewhere. Should be here. Here we are. So here you have a high Reynolds number problem. You can't resolve the boundary layer. Then here you have a list of typical wall functions. You have to specify for the eddy viscosity, nu t, and for your different, say the K, the Q and R, that will be some models we haven't even talked about. Well, the R, that's the Reynolds stresses actually. But think of it for the K, epsilon, omega, nu tilde, some models use that one as well. But it's these three normally that you will use. So here you have the name of these typical wall functions that we are going to use as a boundary condition for these quantities. If you have such a low Reynolds number that you actually can resolve the boundary layer, y plus smaller than 6, then he suggests typically natural values here, 0. I mean, the turbulence should be 0 when it's laminar, and on the wall, the velocity is 0, hence it should be 0. Normally, they say, don't use 0, use a small number instead, 10 to the power of minus 10 or something. Because sometimes, remember these models, they divide by these quantities, so it might explode. So use a very small number. Yeah, y plus and y plus. And then we have the problem. Before you start the simulation, you have no idea what's my y plus going to be. You can choose a mesh, okay, but what is y plus for my cell closest to the wall? So yes, you can estimate it, maybe easier, do a simulation and see what they report, because we can find a way to get these y plus values after a simulation is done. So we can investigate it afterwards. That might be easier. As an estimate, sort of have a recipe here. So this demands that you actually know your bulk Reynolds number based on the mean velocity. So if you have an inlet velocity of 1 meters per second, then you can then you know your Reynolds number before you start the simulation. But if you have another problem, like I put in a force, pressure difference, then you don't know the velocity before you begin. Then this can be hard to find. Maybe you can find an estimate for it before you start, but not so easy. But if you know it, okay, then you can use these, say, empirical recipes that we have here for the skin friction. And from that one, you can find an estimate of what's the wall shear stress. From the wall shear stress, then you can get an estimate of this skin friction velocity. And then it's possible to have your distance in meters to your first cell. and translate it into non-dimensional plus units. So that is one recipe. So normal to the wall, yeah. Then you know now we have to go either under 6 or have to be above 30. In the other directions, well, they can actually be fairly big, streamwise, along the wall. Then they can be, say, the X plus here, it could be 100 times this one. So the cells here can be quite elongated along the wall. That's okay. Yeah, some tips. And here we have a couple of commands that might be good to know. We have a quick and dirty way to sort of make these cells close to the wall smaller. So that was your question. If we can just use crude, say, refinement close to the wall. This is the way to do it, so you can try it. But be careful using that one. That's something you're going to play around with in exercise 2 anyway. And then also, yes, we have the possibility to find the Y plus from open form, that we can report it. I'll show you later. And then finally here is just some nice images. Flow around, say, a square cylinder. This is a large eddy simulation. Remember, for a large eddy simulation, what was the rule? It had to be 3-dimensional, it had to be transient. So this is just a snapshot. So you see a lot of structures here. And yes, these structures will then obviously change with time. If you had simulated the same with an Rans model, he will model all this turbulent motion away and just have a steady state solution. And then actually it could be done in 2D. I think it's a color further down here. Again, this is a large eddy simulation, a little bit instantaneous velocity or and vorticity. And you see the mesh they have been using here. This is your square cylinder. You see they have really refined it very close to the wall. This actually is a terrible mesh. Remember, you have a flow coming in here from the left, going around this, square. And here you will then have a velocity with a very small delta x. Oh, that's going to be expensive if you're running a transient simulation. Because you have something called a Courant number, and the Courant number should be actually smaller than 1 in an ideal world. So here you're running into trouble. You have to use very, very small time steps. But with a large eddy simulation, you have to use a small time step anyway. But such a mesh for using a Rans simulation, I won't recommend it. At least not a transient simulation. So here you see the difference between large eddy and then a Reynolds average Navier-Stokes. Here you have a lot of details. This is just a snapshot, the solution in a plane. And here you see everything is just smoothed out, sort of only average values. So here you have the details. Here we have modeled the details away. Okay, then let's see now. You had been given exercise 2. So we are going here to simulate the flow over a backward facing step. It's a classic problem. And we are going to compare this solution with an article. They have done a DNS actually. And it's a fairly decent DNS. The article should be here. And actually the information you need here is the Reynolds number based on the inlet, the step height, 5,100, so it's just turbulent. And the reattachment length 6.28. That's the only two numbers you need to know from this article. You can have a look at it, how they have done it, but it's quite heavy. And as I said, when you do a DNS, you have to do it in 3D, although the problem actually is only two-dimensional. So, I mean, in the Z direction here, nothing happens, does it? Well, in a DNS it does, but not for a Reynolds stress model. So, yes, we are going to do this in 2D, not in full 3D. You have then been given a block mesh dict file. So you don't have to punch that one in for yourself. I just made it very, very simple, 3 different blocks. So use that one and use the pitch daily steady case. Now, depending on your version, your distributional open form, it may be called only pitch daily or pitch daily steady. We can have a look at it later. So this is the mesh, and also the top wall here should be a symmetry line, not a solid wall. The solid wall is only downstairs, backward facing step. And here you have some nice commands that you should be aware of. After you have done a simulation, you can execute this one, a post process, and then minus the function y plus. He will then report what's the average y plus, what is the maximum y plus, and you can even have a look at them in ParaView and see along the wall where are the y plus big and where are they small. You also have this refined wall layer, as we talked about. You can really chop up your mesh close to the wall if you want. Then this will be the syntax. You have to put in a number here. If you put 0.5, then he will split the cell closest to the wall in half. So that might be a little bit too crude. I put in some optional extra questions here, but this is something we have to talk about later, actually, next week. So this is not necessarily so easy. So I just put it as an optional extra. Okay, let's have a look at the pitch daily case. Let's see, I have Ubuntu here. Thank you. Open from 2312. And then I go to my run folder. Now you have to find your pitch daily tutorial and copy it into your run folder. In my distribution, I think it was under opt, open form, wasn't it? No, big O, no, it wasn't. Let's find it. Echo, and then a $ form tutorials. Oh, it was under user lib. Okay. Copy -r / user lib, and under lib it was open form, wasn't it? Yes, should be. Open form, and here I should have tutorials. Under tutorials, I find it under incompressible, and under incompressible, I will now have a program, not icoform, that was what we used when it was laminar. You use simple foam. Under simple foam, you will then find the pitch daily case. So let's have a look at that one. Pitch daily, and under pitch daily, we actually have another pitch daily. Okay. No. No, there we have it. 0, constant, and the system folder. So that is my case. And then space and a period. So that's the command. Copy recursively from this address to where you are standing. Like that. So now I have a PIDS daily setup here. It's a standard minimum setup. You have a 0 folder, constant folder, and a system folder. Let's have a look at the different files here quickly. Gedit. Let's start with the big boss file, the control dict. And the control dict for this case looks something like this. As an application name here is called simple foam. Depending on the distribution, it may be something else. But the program is actually simple foam. Never mind. Simple foam, start from start time, 0, end time, 2000. That's a big number. And then look at the delta t, it's 1. This is a hint. Simple foam is a steady state solver. He doesn't solve it in time. But he uses time, say, as an iterative dimension, so you don't get the real time history here. You're not interested in it anyway. I want a steady state solution and nothing more. So the idea is you put a big number for end time, and then you start the program. He will automatically stop when he has found a solution, hopefully before he reaches 2000. If he reaches 2000, then something may be wrong, or maybe you have to increase the number. So that is a steady state setup for you. Okay, let's just try to do this quickly. We have a block mesh. Block mesh. Thank you. And no arrows here. We have an inlet and outlet, upper wall, lower wall, and we have front and back. As also a hint, front and back, it's a 2D case. How many cells do we have? 12,000. Not that big. If you like, it's a good idea actually, check the mesh with the script check mesh. And he should then report mesh OK. So yes, it's good to go. Then let's try to simulate it. Simple foam. Takes some time, but shouldn't take too long. Here we go. He used 281 time steps. Remember, it's not real time. So it's just an iterative dimension, you might say. And what has he done? He finds the velocities, he finds the pressure, he finds the epsilon, and he finds the k. This is a k epsilon model. What do you know? Okay. Goody, goody, goody. What have we received? Yeah, you have some couple of time folders here, time result folders, but it's only the last one that is of interest. I mean, you don't have a real development here that's physically correct. It's a steady state thing. So now, para foam, just to have a look. Apply, and then here we have, say, the velocity, and we can play it to the end. There you have the steady state. So you're sending in a constant velocity here, and here you have the backward facing step. And you can actually think of it as a streamline starting here at the corner of the step. He will then stop somewhere here, somewhere. Because here you have one big vortex. And this distance, scaled for the time step, there you have your reattachment length. That's the one we are seeking. If I want to find it here, I can actually do that by using plot over line. And then, well, you can actually use the mouse here. And then put this line, say, a little bit above the bottom. Something like that. and then apply. And then he has plotted a lot of different things. I'm not so interested in all of them, but I want the velocity in the x direction. I don't need the epsilon. I don't need the k. I don't need the eddy viscosity. And I don't need the pressure. There I have the velocity alongside this line very close to the bottom. So you see he goes negative. Makes sense, since you have a vortex here, you have a velocity in the negative direction. The question is, where is he zero and becomes positive? That's the reattachment length. So you just hover the mouse here. Don't have to click on it, you just hover the mouse, and there you have the location. Okay, so roughly there, I have an x position of 0.18 meters. I think the step height here was 1 inch. So then you can calculate what's the reattachment length. So that's an easy way to do it. Okay, I won't go through all the details here inside this Pistelli case. We're going to look further into this in the next lecture. But at least you should have enough here to get exercise to start it. Any questions? Then we take lunch.